everybody to the welcome everybody to the last day of the conference of the workshop. And let me just remind you once again that this meeting is being recorded. So when you want to ask a question, which you're very welcome to do, and you ask it verbally, I mean, of course, you will be recorded, and we take this as your consent that it will go online as well. And with this warning, I am very happy to now hand over to Miranda Cheng, who will tell us about, or who will take us to the limit, quantum modular forms in moonshine physics and topology. Please.
Yeah, great to see you all, and thank you for the invitation to speak, and especially thanks the organizers, all of you, for putting together this wonderful program. I've been enjoying the talks a lot, although not always, live. Sometimes I fall asleep at midnight, but nevertheless. Okay, so the title of my talk is going to the limit, and now I'm going to talk about quantum modular forms, which we have heard about already in quite a few talks this week, in places such as moonshine and topology and physics. So let's start with our favorite place of the workshop, the upper half plane, which of course admits an action of the modular group SO2Z, actually the whole SL2R. And to set the notation, let's write an element gamma of SO2Z in the form of a 2x2 matrix, and then of course it acts on a point in the upper half plane in this familiar fractional linear transformation. Okay. And now let's look at the boundary of this place, which will be our favorite place in this hour, the boundary of the upper half plane. And we see, of course, that it has points at I infinity, and which is equivalent under SO2Z to all the rational numbers. In other words, SO2Z acts on these, and in fact acts on this transitively. So every point is, there's one cusp as far as SO2Z is concerned. And as I just said, the word, we'll call these the cusps of the upper half plane. And these cusps, they correspond to, well, different things in different contexts. For instance, the degenerate limit of a two-dimensional lattice or an elliptic curve. Or in physics, they correspond to, for instance, I infinity, the low temperature limit, and the behavior near the cusps, or the boundary condition of a modular form often determines, for instance, the growth of its Fourier coefficients via what physicists call Cardy's formula, or the more precise version, the Rademacher formula, etc. Okay, so then that's what we're interested in. We're interested in taking the limits, okay, from the upper half plane to, for instance, a rational number. And well, using our usual exponential map, Q equals 2 pi I of tau, this corresponds to approaching a root of unity from within the unit disk. So this limit is sometimes called the radial limit of going to the cusps. So for instance, then consider a function on the upper half plane, well, which is bounded near the cusps. So with f of I tau, so this is the formula for the limit we're taking. for all the cusps, for instance, then we can define from it, I'll call it the f check, a function on the rationals by defining f check being just the limiting value, okay, of this function on the upper plane. And then we want to ask ourselves what this function, what kind of property this function on the rationals can have. So for instance, if let me know if I'm writing too small or something, or too unclear or something. Okay, if f, this function on the upper half plane, is a modular form, and here in this occasion, I do not need to define what a modular form is, but just to set the notation, it is a function on the upper half plane that's holomorphic, and then which is invariant under the slash operator, okay, of weight W, which is defined as in this way, okay. For all elements gamma of your favorite group, which I'll take to be a subgroup of SO2Z. Okay, so if F is such a modular form, then we see that a resulting function F check has the following property. Namely, if we define, let's say, this co-cycle, which we have already seen in previous talks, and probably will see again in the next talk, the co-cycle, which measures, you know, the difference between the value of f check and its modular transformed version, then from the modular property of the parent function f, we know that this co-cycle vanishes, okay? All right. And that's nice. And this vanishing condition is the condition that we would seek to generalize later. But first, okay, let's consider also something else, which is a slight generalization of the notion of modular form, which is the weakly holomorphic modular form. What are they? So we let the function to have exponential singularities near the cusps. Okay, so for instance, when the group is SO2Z and the weight is 0, then we have the famous J function, which has the following form, the following Fourier development. And it is, of course, invariant under SO2Z. Okay, so it is, I'll call it optimal, okay, in the following sense. In the sense that if you want something that's invariant under the SO2Z transformation, and that is not a constant function, then you need to have poles. Okay, you need to have singularities. One way to see this is because you're mapping this, okay, the keyhole fundamental domain to CP1. And if you want it to be non-trivial, you need to have a point that maps to infinity. And this is basically up to an additional constant. This is the unique optimal such choice. And the optimal just means that the singularity is just q to the power inverse, okay, instead of q to the power -2 or -3 and so on. And famously, it also has the moonshine property, namely that these numbers, okay, Fourier coefficients are dimensions of certain distinguished representation, which I will denote V sub n natural of the monster group, okay? So this is distinguished, I won't go into the detail how distinguished, but module for the monster group, which is the largest finite simple group. Okay, so you see that apart from homomorphic, nice behaving modular forms, we also have weakly homomorphic modular forms. Okay, now let's come to a related notion, that of a Mach theta function. So Ramanujan wrote them down in the form of Eulerian series, just to take an example, a specific example, an order 7 example. Okay, I add this q power to let it transform nicely. So q to the n squared. Oh, here I failed to write it. I don't know how to, sorry. I don't know how to click it away, the thing that's, anyways, the art of keeping up with different Zoom versions. Anyways, now I can write, okay? So it's an infinite sum of the following form. And that's how Ramanujan first wrote it down. And you can see by eye that it has a few very nice properties. For instance, the coefficients are all integer. So, and they have very slow growth. Okay, and we can also see that it has, you know, some singularity at cusps. Well, here you can see that from leading power that it's singular at the I infinity cusp, but you can also see that in other rational number cusp. So in his last letter, Ramanujan asked the following question. So he asked himself, given such an Eulerian series, okay, is there a modular form, I'm paraphrasing his letter, from such that the difference between the two is finite at all cusps? And he then answered his own question saying not necessarily. And he said, when it is not, I call the function a Mach theta function. Okay, so this not necessarily was proven by Griffin, Ono, and Roller. They have proven that let f be any of the Mach theta functions that Ramanujan wrote down, then indeed there is no weakly holomorphic modular form f prime such that the difference is finite at all cusps. Okay, nice. So Ramanujan was right in his letter. And how did Griffin, Ono, and Rowland prove this result? Well, in fact, they have used the what we call the modern definition of a Mach modular form, generalizing the idea of Mach theta function. So again, this is a place where I do not need to define such a thing. So let me just be really brief. Well, if this is a homomorphic, f is a homomorphic function, and we say that this is a Mach modular form of weight W and possibly with a multiplier. Anyways, if there is another function, a modular form G called the shadow, as we have probably all heard about, such that we can define its completion as the linear combination between the original thing and the non-holomorphic Eichler integral of G, this modular form, this which is defined in the case where G is a cusp form as I promised, a non-holomorphic integral that we say to be such an integral such that this completion then transforms as a modular form. Okay. Okay. So using this, and in particular the Grenier-Funke pairing, the Ramanujan's claim on the behavior at the cusp is proven, and the corollary, in fact, if we use this definition, is that there is, however, a set with cardinality necessarily larger than 1, such that for all cusps you can find one of the elements and to subtract it, okay, where each of the element is a weakly holomorphic modular form. Okay. Any question? So when T is 1, such a set doesn't exist, but there is a set with cardinality larger. Okay, basically you can just count the inequivalent cusp, and that's going to be the upper bound for T. So in this case, then we can again define a function f check on the rationals by taking the radial limits. Oh, it doesn't let me write again, but okay. So f minus f prime j of x, we already said that this is bounded. Okay, so you just take t, the imaginary part to vanish. Okay, and then you again define from a Mach modular form of weight, in particular here weight 1/2, a function, well-defined function on the rational. Okay, so next I would like to ask a question, namely, well, that's nice, all these Ramanujan's function, they have integral coefficients, they have slow growth, and are there other Mach modular forms, in particular in weight 1/2 like this? And we know that low growth means that we have to look at the behavior of the function at the cusp. So, okay, in order to answer such a question, okay, let's just define something Jacobi. Well, this is this, I'll just write down the standard definition of the two-variable Jacobi theta function of one dimension. Okay, y is e to the 2 pi I z, and we'll also define the usual one variable theta function as, you know, coming out of this Jacobi theta function by possibly taking a derivative and then put Z to be 0. Okay, so when I is 0, it's a weight 1/2, and I is 1, it's a weight 3/2 theta function. Okay, so that's just definition. Now we consider what's called the mock Jacobi form. Okay, so namely, we consider a vector of mock modular forms and with a vector of shadow and the corresponding completion as before. And it's said to be a mock Jacobi form, this big F, if, you know, when we take the completion to be the theta coefficient, then this transforms as a Jacobi form, and in particular in weight 1, because we care about the weight 1/2 mock modular form. So in order to have something that looks like Ramanujan's mock theta, we want to impose again the optimal condition, namely, well, one idea would be to require that it's bounded at all cusps as before. But it turns out that there's no solution when F has weight 1/2. Okay, you can prove that. So the best you can do is in fact to require this. When its pole is extremely mild, so if you add, you know, multiply by an additional power factor of Q to this small power, then it's indeed finite at all cusp. Okay, so this is a good definition. And it turns out that there are finitely many of them, well, up to, you know, trivial equivalence given by multiplication. So the paper was published last year. So the first results, well, to answer the question about what other mock theta function like functions are there, the result is that, okay, if we want an infinite Q series with integer coefficients, then its shadow has to be in the span of weights 3/2 unary theta functions like this. So that's, in some sense, they are all mock thetas, okay, in this precise sense. Well, of course, this left arrow going left requires some, you know, multiplication, but you know what I mean. Let me know if you're not sure what I mean. And moreover, in fact, for all m possible m, which is the index of the Jacobi form, there are in fact finitely many 39 such optimal forms. Okay, and all of them, as promised before, have integer coefficients, so I don't need to write again. And this 39, they correspond 1-to-1 to the 39 subgroup of SL2R that define a genus zero quotient on the upper half plane. So in other words, its fundamental domain on the upper half plane is genus zero, is a genus zero Riemann surface up to finitely many points. Okay, so this K, I'm not going into the detail, but there are some Akin-Linear involutions, and they're determined uniquely by the symmetries of this AF vector value function. Okay, so that's what we have shown, the classification of such nice functions with optimal behavior. Oh, by the way, the this optimal condition was also extensively discussed and utilized in the paper by De Boker, Murthy, and Zagier. So, the first remark is that indeed, most of Ramanujan's Mach theta are realized as the components Fi in one of these 39 optimal forms. For instance, the Eulerian series I showed you earlier is the first component when, you know, the index is 42. And then I would like to go to the next comment, namely the discussion of relation between optimality and moonshine. So we have seen that in the world of modular functions, the unique optimal forms are what gives you, you know, the monster moonshine. So the J function is optimal, and its corresponding McKay-Thompson series, the twine function, as well, in a very concrete way. And in fact, we have found 39 functions, well, in our classification, which contains exactly 23 with all positive coefficients. Okay, up to the leading term that I'll explain later. And these are precisely the 23 sets of functions corresponding to 23 cases of what's called umbra moonshine, which contains, in particular, the mature moonshine that you have heard about in the talk by Jeff and Antarmi. So, for instance, let's write out that that corresponds to the index 2 function, and if in that case is given by 2 minus 1, always there's a minus 1, that's a unique function with negative coefficient. All the rest is indeed all positive, and that singles out these 23 cases. You have seen this function for a few times by now, I believe. So apart from this initial term, and you can show that this is indeed the dimension, greatest dimension of a particular module of the mature group M24. So the classification of optimal forms, if you want, also explains what's the property that distinguishes these functions appearing in Umbrelmunstein. Okay, so now I would like to again continue my study on, the optimal behavior. But instead of weight 1/2 Mach modular forms, now let's look at weight 3/2 Mach modular forms. So now
Miranda,
consider, yeah. Hi, Jeff.
Before you go on to weight 3/2, do you or you and John or somebody else figured out whether the non-umbral optimal weight 1/2 forms exhibit some kind of moonshine?
Yeah, the belief is yes, but John and I think one day we'll figure it out, and you know what
But
it means.
they presumably would be for small groups, so it's not obvious from the coefficients what. Yeah. Okay. Thanks.
That's right, and they and also they probably correspond to some much more exotic lattices, because as Jeff knows more than anyone else, these 23 cases of Umbrelmunstein corresponds to 23 Niemeyer lattices in 24 dimensions. Okay, so now consider weight 3/2 case. So that would mean, let me click this away so I can write. So that would mean weight 2 Mach-Jacobi forms. So you might try again the optimal condition of again, they should all be, finite at all cusps. But it turns out that just like in the weight 1/2 case, it's not such a great condition for the opposite reason, namely there are infinitely many, too many solutions. So, well, let's give one example. So this is the Hurwitz number function that has appeared in many talks already, and talked by Boris, by Greg, and by Katrine, and probably by other people. And now this is the Hurwitz number. So we said that it's 0 or minus 1/2, or indeed the Hurwitz class number, depending on the sign of the discriminant. And this is Mach-Jacobi form of weight 2 that's finite at all cusps. That's one example. So now let's again refine such an idea of optimality. So we say something is alpha optimal for alpha real number, we take it to be an integer number, such that, excuse me, yeah, okay. It will be finite for sure, and in particular, it will be, it will take the value minus alpha when tau approaches the I-infinity cups or its equivalent, and 0 and vanish otherwise. So it's a much more restricting definition than just requiring that they're all finite. Okay, so then what do we find? What can we learn using this definition about optimal functions at weight 3/2? So it's not published, but many of you probably have heard one of us talking about it before. So we found that such a definition leads to some quite interesting relation to, again, to finite groups. So let's take the simplest finite groups, which is the cyclic group of prime order. So n is the prime. Okay, so then the result is that the smallest alpha, which we take it to be positive, such that there exists a virtual module for G. Virtual just says that the vector spaces are Z2 graded. They can come with a plus or minus sign. And we denote this module for G by W module, W of G. Okay, and again, it has this Q grading, such that, well, the graded character, so small g is an element of G. So here you just have two types of elements, the trivial one and the generator of Z mod N. Okay. Such that this, okay, graded characters are alpha optimal mock Jacobi form with, in particular, the identity is just given by a multiple of the Hurwitz number function. And the result is that this number, alpha, the smallest possible number, is given by this very simple expression, which can be interpreted in terms of the torsion points of the Jacobian of the modular curve defined by gamma 0 big N. But we're not going into that detail later. Okay, so for all cyclic groups of prime orders, you can come up with a G module based on the Hurwitz number. So this has very interesting and systematic almost connection to finite groups. And the second result I might want to highlight today is that alpha is 2 for the finite group N11. And if you want, alpha is 4 for M23, which is a smaller close cousin of the Matu 24 group. And it's not really a corollary, so let me just write it. A consequence of number 2 is the following. And here you can see that some, unexpected connection to other parts of mathematics coming in. So let me just state it. So, okay, these negative discriminants, and for some reason I can explain to you, we want D to be, 21, not 24. Okay, so that's D. So for such D, if there exists a alpha equals 2, so this is our optimal alpha, optimal M11 module. So this is, we call it this. Such that, okay, so such that at discriminant D, this vector space contains a specific irrep of M11. So I call it chi 20, chi 55, because the dimension is 55 and it's an irrep, and then that's uniquely specifies it. Okay, then this D is not a congruent number. So what is a congruent number? Is a number which is the area of a triangle with right angle such that all three sides are rational numbers. For instance, 6 is a congruent number because we have 3, 4, 5. This, okay. Okay, so this is quite interesting. So by some properties of the module for a finite group, you can actually prove something interesting about arithmetic geometry. So, and similarly, you can play the same game for M23 and so on. I won't be able to, I'm not planning to go into any detail here, but let me just say that's an interesting and important element of the proof is by tunnel, which relates, okay, the congruent number to the rank of some D twisted modular forms. So to some way 3-hops modular forms that encodes the certain the behavior, the rank of a certain elliptic curve. Okay, so that finishes my exploration of you know, the optimal forms and moonshine. So now let's take a closer look at the limits of the mock modular forms.
Sorry, may I ask a question?
Yes, Amir.
Hi. Can you just flash the definition of your alpha optimal? I think it went past me.
Yeah, so alpha optimal is here. Yeah.
So F goes to a constant at a cusp, is that it?
F goes to a constant alpha at the cusp, and 0 and vanish. F has to vanish.
And alpha some real number, or?
Yeah, alpha is a real number.
Thank
and
you.
we will take it to be integer because we want vector space interpretation. And this, of course, has to hold for all elements, for all components of the vector value guide. Okay, so I will go on and explore the worlds near the boundary. Are there further questions? So consider a weight. Now let's go back to the world of weight 1/2, just for the sake of concreteness. And we say that we can find a set of weakly holomorphic modular forms such that for each cusp there is, you know, one of them which cuts out the singularity, and then we can have in the neighborhood we can have a asymptotic expansion like this. And from the definition of mock modularity, the modern definition, it's not hard to see that in fact the thing you added to or subtract rather, the non-holomorphic isolar integral, in fact have the same expansions. Okay, so I think, you know, I'm not sure what the best references for this fact, but it's certainly contained in this paper. And then when we take t equals 0 and recall that we define this, this function defined on the rationals. So now let's again look at the co-cycle of this f-check function, which used to vanish if f was a modular form. So just recall the definition for a given f-check function defined on the rationals. So now it no longer vanish, and instead, we can replace f-check with g star because of the fact that I just said, and we replace it with a g star, then given the form of the non-holomorphic Eichler integral as an integral, we see that this co-cycle is now in fact given by a period integral, which is clearly nice in the sense that, for instance, is real and analytic in X. So this shows that, this function f-check is a quantum modular form. So, well, we have heard the definition before, but let me just briefly recall. A quantum modular form is a function on the rational such that the co-cycle is nice, okay, and real analytic is nice enough. Okay, in fact, well, I've been saying too many facts, but actually, so there is a close cousin of what we have said above, is a closely related behavior near the cusps. And this is given by, what's called the holomorphic Eichler integral of a modular form G. We'll denote it with G tilde. So now it's indeed holomorphic well, okay, if G has weight W, then this is minus of 2 minus W equals W equals 2 minus 2. So let me okay, so what do I mean that they're closely related, apart from the obvious fact that they're both given by similar looking integrals? Well, in fact, they have the same quantum modular properties in the following sense. Recall that if I have a Mach modular form and I cut out the singularity with a modular form, and it has this, asymptotic expansion, just like G, the companion does. So with the same G, but now consider the holomorphic Eichler integral instead, and consider the opposite cusp instead. And you get an almost identical asymptotic expansion, okay? So it is as if the two functions are somehow related by a change of sign of tau. So an example of such an holomorphic Eichler integral is when you take G to be the unary theta function that I defined earlier, then the resulting function is nothing but the fourth theta function that we have heard about in, for instance, Katrine's talk. So the difference between the false and the usual and the true theta function again comes in this sign. Okay, so that's interesting because we have seen that these optimal forms, in particular one of any of these 39, they have the shadow G that's given by something linear combinations of this. So it's almost companion on the other side of, you know, the world is supposed to be given by such a full theta function. Well, in fact, there's two ways to make this more precise, but I think I'll skip the detail because I do want to go to talk about other things. But the first way is if you perform a Rademacher sum or some regularized Poincare series, however you want to call it, and you arrive at a modular form, Mach modular form on the other side, and you perform the same Rademacher sum on the other side. It involves changing the order of like expansion in the middle of a calculation. Then indeed you do in fact get a shadow, the holomorphic partial integral of a shadow. So you can read about it in my paper with John Duncan in 2012, for instance, although I mean I'm sure it's known by some previous paper. And the other thing is Eulerian series, many of them can in fact be also determines something well-defined outside the unit disk. And in that case, in many cases, you can indeed show that outside the unit disk, you get instead this full theta function. So, okay, you can ask me about details in that later about. So.
You have about 5 minutes left, by the way.
Yeah. So my last topic will be, you know, how these behaviors at the cusp show up in the natural context, namely in the context of three-manifold invariants. So let's recall that given a three-manifold, and let's take the gauge group to be SU2 for now. And we have the so-called Witten-Rashtikin invariance, which is a function on the integers. And what is it? Well, it's basically up to some normalization, the Chern-Simons partition function on M3. This gauge group is SU2. And then the K is, if you want, is the effective level of the Chern-Simons function. Okay, so that's what it is. And it is, importantly, a topological invariant of M3 that can tell you if the two three manifolds might be the same. So now it's a bit of a bummer that they only depend, you know, it's only a function on such a discrete space. We would like to instead have, you know, a Q series and maybe to categorify it to get better three-manifold invariants. So the work by Gukov and Putrov, Pei and Vafa is that they propose that there's indeed such a Q series invariant which is, if you want, the path integral, the partition function of a certain three-dimensional theory labeled by M3 that can be obtained from compactifying M fibrates. And with on this space-time is GAR times a circle with the boundary torus. That's has a complex structure tau. That's the variable here. And on this boundary, I have to choose the boundary condition, and this labels the B. Okay, I won't have time to go into it. And as usual, it also has a vector Hilbert space interpretation so that it counts BPS states. So it's indeed a Q, it should be a Q series with integral coefficients. And the conjecture is that it's related, okay, to the Chern-Simons partition function as some kind of a sum of these Q invariants. Okay, so the sum is, okay, so the sum is not here. Instead, what I meant is that we have to take the limit. The limit is indeed the radial limit we're looking at of tau going to approaching 1/k, 1 over the level from within the unit disk. So here we can see that if I look at, if I take the cusp to be 1/k and take gamma to be the S transform and look at its co-cycle of this function, okay, that it has the interpretation that this would give the Zeta point contribution, and this will be the perturbative contribution in the limits, classical limits of k going to infinity. So here the quantum modularity is expected, some sort of a quantum modularity is expected for the function, for the three-manifold invariants, because it's, you know, we wanted to have the trend series expression in the form that's inspired by physics. So I will skip, but that's given the physics definition from this Z hat, but for some subsets of three manifolds, we also have a mathematical definition for which the conjectural relation to Chern-Simons is proven. Okay, so now let's look at special examples and then see if indeed we get quantum modular forms of some kind. So here I will just list a list of results. So assume that M3 is of certain type. I skipped the last slide, so we don't need to know this. So that's such that this invariant has a mathematical definition, we can just go and compute. Then if indeed, in particular, it's a cipher manifold with 3 exceptional fibers, then you can actually show with this, with a certain choice of orientation for this M3, that indeed they are these 4 theta functions. So the first hint went all the way back to Lawrence and Zagier in the context of Chern-Simons WRT invariants. And for general cipher manifolds, so you don't have to have this constraints where there's only 3 singular fibers, and you actually get the linear combinations of 4 theta functions and its derivative, and also, you know, isolate integral of the other the usual theta series, which is again a quantum modular form, as we mentioned, and its derivatives. So there indeed are quantum modular forms of some kind. And the new result is that what if we generalize it to SU3, but we keep the simplest examples of M3, then it's as we have heard from Patrine's talk, it's quite a challenge to study it, but you can prove that it's indeed a quantum modular form of depth 2. So since we have heard the definition before, I won't repeat it. And I'll totally skip this part, but there's also a very interesting relation to characters of log VLAs. And finally, well,
Miranda, are you keeping an eye on the time?
Yeah. This is my second last slide. Okay, is that all right?
Yes, please wrap up.
Yeah. So, okay, we have talked about this before, so this is a repetition. So finally, because we know that if we, so if we change the orientation of the transaminds, then of the three-manifold, what it's equivalent to changing the orientation of the level. So what we expect is that to have like a tau going to minus tau transformation. So from what we have discussed before, the conjecture is that if on one side, on the one side, it is a false theta function, then on the other side, it's a Mach modular form with the corresponding shadow. And you can actually try to define this mathematically, this z-hat invariant using indefinite theta series. And similarly for higher depth cases. So this is the end of my talk, and I'll leave the conclusions for you to read. Thank you very much.
Thank you very much for the very nice talk. So if there's a very quick and urgent question, maybe we can have it.
I have a question. If it's not quick or urgent, you can one of you can postpone it, yeah. Either the organizer or the speaker. The last thing you showed about the Chern-Simons theory in physics defining quantum modular forms a few slides ago. What is the niceness condition for the perturbative series?
Well, so far it has to be real analytic because it's a perturbative expansion, so it's kind of a asymptotic expansion, if you want. So that's what we expected, but I mean, higher depths quantum modular forms also work out nicely. I mean, it also has natural interpretation in terms of the trans-series expansion. It just says that there is a more complicated, increasingly complicated power series multiplying your exponential set of point contribution.
I see. So roughly, it extends to the real line. Is that the statement? The
real line?
It extends to the real line in a nice way. Is that the statement?
It extends to the real line. It extends to the neighborhood. Yeah, not necessarily. It's a real line. It's really a asymptotic series. So it doesn't really have to be real.
Okay, maybe I'll ask you for more details. Thank you.
Yeah.
Okay.
So you can think about it as this T also, if you want. That's also possible.
Okay, thank you. Yeah, I think we should move on. We're already a bit behind. Thank you very much again, Miranda, for the talk.
You're welcome. Thank you.